Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 4.80. The problem statement says, fuel oils contain primarily organic compounds and sulfur. The molar composition of the organic fraction of a fuel oil may be represented by the formula carbon P, hydrogen Q, oxygen R. The mass fraction of sulfur in the fuel is XS, so kilograms of sulfur per kilograms of fuel, and the percentage excess air is P sub XS, is defined in terms of the theoretical air required to burn only the carbon and the hydrogen in the fuel. Part A. For a certain high sulfur number 6 fuel oil, P equals 0.71, Q equals 1.1, R equals 0.003, and the weight fraction of sulfur is 0.02. Calculate the composition of the stack gas on a dry basis if this fuel is burned with 18% excess air. Assuming complete combustion of the fuel to form carbon dioxide, sulfur dioxide, and water, and expressing the sulfur dioxide fraction as ppm, moles of sulfur dioxide per million moles of dry gas. So to start off with, we need to draw our picture here. I wrote down the information they gave to us. We have this chemical composition of the organic portion of the fuel. And then we've got our weight fraction. In the problem, they use an X. I always use X to represent a mole fraction, so all of my weight fractions are lowercase w's. Okay, so this is the weight fraction of sulfur in the fuel. Okay, and then this is the percent excess air. Okay, and that only includes the carbon and the hydrogen and not the sulfur. Okay, number 6 fuel has these properties that they gave to us. Okay, so we've got fuel going in here. We have a certain percentage that's organic, and we have a certain weight fraction or percentage that's sulfur. I'm going to say I have 100 kilomoles of, let me see, I've got that. Yeah, I need to change that. That's not of fuel, that is of organic. Okay, so the way I wrote this problem out, I said that the weight fraction of organic times the molar flow rate of stream 1 is equal to 100 kilomoles. So that was my basis. Okay. And that made calculating the excess air easy. Here's another part where we balance this equation. Okay, so right here, we're balancing the equation right here. In order to balance this equation, all we know are these quantities, right? And we need to know what these are, right? So if you watch my other videos, you remember how to do this. First, you balance the carbon. So I write down how much carbon is over here. Then you balance the hydrogen. So then I balance hydrogen over here. There's 2 hydrogens in water, so this is divided by 2, right? And then you balance the oxygen. You say how much oxygen is over here. Well, we have this much times 1, and then we have this much times 2. You add all that together, and then you divide it by 2 over here after you subtract that out. And I may have forgotten to subtract this out. Okay, so these numbers are slightly off. This number should be 3.5. Okay. and then that ends up changing a bunch of this, because I forgot to add that in. Okay, so you have to make sure you add that in. It's a really small amount, but it makes a little bit of a difference in the end. So my numbers will be slightly off for this, but you just change this part to do that correctly, and then your numbers would be a little bit different from mine when we're talking about how much air is being pumped in. Okay. Anyway, let's move on from there. We've got our total oxygen that we burned. We're starting off with this much organic. So then we have this many moles. Again, my number is going to be slightly off, but that equals this many moles of oxygen per hour, right? Then we have total air. That would be the total amount of oxygen divided by 0.21, okay? Then that equals the total air. Excess air equals total air times whatever the excess percentage that they gave to us. That's what that is. Okay. And then this equals N2 in our drawing, right? So we have N2, a certain amount of moles going in here. That is how many moles of air we have going in. Okay. Now we need to do the burner balances. Okay. So we say, okay, we've got this organic composition, we've got this flow rate, and this does not include the sulfur, right? Okay, so we'll do our carbon balance. We say we have this much carbon going in, and we have this much carbon going out. We have this much sulfur going in, we have this much sulfur going out. We have this much. So if you have for every 1 mole of the organic, we have 1.1 moles of hydrogen. For every 1 mole of organic, we have 0.71 moles of hydrogen. Carbon, that's where those numbers come from. Okay. And then for every mole of water, stream 4 is the water that comes off, right? We have 2 moles of hydrogen coming off. For every, okay, so we've got a certain amount of nitrogen going in the air, and then we have a certain amount of nitrogen going out the stack. Okay, that's what that one is. For every mole of oxygen, we have of oxygen gas, we have 2 moles of oxygen atom. Okay, then we have a certain amount of oxygen going in the organic, right? So for every mole of fuel or organic, we have 0.03 moles of oxygen going in, and then alongside that we have a certain amount of oxygen going out the stack, and then we have or out with the water. This is the water, and then we have a bunch going out the stack. So we have some going out with oxygen gas, so it's got a 2 there. We've got carbon dioxide, that means there's a 2 there, and then we have sulfur dioxide, that means there's a 2 there, right? Okay, so we need to convert mass into a mole fraction, right? So we wrote all of our balances in moles now, but all of our information about sulfur is in weight, right? So now we need to convert this into a molar balance. Okay, so we've got our molar mass of organic because we know the composition of the organic, right? So we've got a certain amount of carbon, a certain amount of hydrogen, a certain amount of oxygen. That means the molar mass of the organic is this. Okay, so if we have this many moles of organic going in, then we can figure out how much mass that is because we know the molar mass now. Okay, so the mass flow rate of organic, or our molar flow rate of organic times our molar mass, gives us the mass flow rate of the organic. Okay, and if there's only organic and sulfur going in, then 1 minus the weight percent of sulfur equals the weight percent of organic. Okay, so if you divide the mass flow rate of organic going in by its mass fraction, then you get the total amount of mass flowing in. Okay, and if you know the total amount of mass flowing in, then you can back calculate what the weight percent of sulfur is. And once you know, or we know what the weight percent of sulfur is, sorry. We know what the weight percent of sulfur is, but now we can figure out what the mass flow rate of sulfur is. And once we know what the mass flow rate of sulfur is, then we can turn it all the way back into moles, right? Okay, so now we have a molar flow rate of sulfur. That's where all that comes from. Our molar flow rate of sulfur is then, this is what it is going in, it equals the same thing going out. So now that's exactly the same thing, molar flow rate of sulfur dioxide as well, okay? Then we've got a certain amount of organic going in. This is our carbon balance, and then we need all of our carbon turns into carbon dioxide, makes that a lot easier. So this is 71 moles, okay? Same thing with nitrogen, that one's really easy. Just whatever's going in comes back out the other side. And then the same thing with our water, all of the hydrogen turns into water. So we just say how much hydrogen is going in, and a certain amount of that turns into water. And you have to make sure you have your stoichiometric ratios here. Okay, so then this is the amount of water we have coming out. This final balance is the oxygen balance. This is the fairly large one, but now that we have all of these other quantities, the only unknown quantity is how much oxygen is going out the stack, right? So we're just interested in that, right? So we solve for what this is, given this equation and all of our other knowns that we have now. And we solve that the total amount of oxygen going out the stack in moles is this. Okay, so now that we have all of the components of the molar flow rates going out the stack, now we can calculate what the total mole flow rate out of the stack is, right? So we have this much going out in CO2, this much SO2, this much nitrogen, this much oxygen. Remember, the water's not included, that's pulled off earlier. This is the dry basis, okay? So we just have this much moles going out. That means the ppm of sulfur is going to be this guy. Okay, and remember, my numbers are going to be slightly off because I used the wrong, I balanced my equation wrong, right? So, okay, so then that's it for part A, and then it says for part B, it's a computer problem. Basically, if you do all of these balances and setups in a computer, if you just keep good track of how you're writing all these down, you just plug in all these equations in a column in your computer, and then you can just, if you do it in Excel, you can just click and drag it over and then change the one value that they're asking you to change. I think it was this value right here, the px value. If you just end up changing that, then all the cascading effects will just change along with it, right? So it's not a lot of work to just plug all these into a computer and solve it that way, and then you can just drag over your answer and change the one value and see the different changes that it makes. So that's what I did. I plugged in their little number, their two different columns. Obviously, if you increase the amount of air, the excess air flowing in, the more dilute the stack gas is going to be with nitrogen and excess oxygen, right? So we've got our minimum excess air that gives us a ppm of 700. That equals 0.936 as a fraction, and then as a percent, it's 93.6%. That's excess air you would need in order to dilute down to 700 ppm. So more air dilutes the sulfur concentration. Okay. Part C, someone has proposed using the relationship between the excess air percent and the parts per million of sulfur dioxide as the basis of a pollution control strategy. The idea is to determine the minimum acceptable concentration of CO2 in the stack gas, then run with the percentage excess air high enough to achieve this value. Give several reasons why this is a poor idea. We did a problem earlier, I think it was like problem number 70, if you want to go back and look at that one, from the same chapter, that kind of discussed this already, but just because you're diluting the sulfur doesn't mean less sulfur dioxide is going out the stack, right? I mean, sulfur dioxide, as soon as you pump it out into the atmosphere at large, the concentration is going to go down. The sulfur dioxide is going to diffuse out into the open air and then just combine with the clouds and, eventually rain down or whatever. So the total amount of SO2 that goes out is still going out the stack, whether you dilute it before you pump it into the air or after you pump it into the air. It's still the same amount of sulfur dioxide. So the regulation is actually not based on concentration of SO2. It's based on how much CO2 you are pumping out per the amount of fuel you're making, right? So regulators do know that it's how much you have going out the stack, not what the concentration is going out the stack. Okay, because in the end, you're trying to protect the environment. You're not trying to hit a standard, right? So the standard should help improve the environment. And in the case of SO2, I think it seems like they've done a good job to make it so that the standard kind of helps improve the environment. We've dramatically reduced acid rain and the problematic effects that come with breathing SO2 as well. So yeah, that's long story short. That doesn't help to just dilute the SO2. All right. Well, that is it for problem number 4.80. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.